What? What is that? Are you computer science major or what? Nine.
Just about there, folks. It's frowned upon starting early, so let's run that clock. And we can begin. Welcome back, everyone. I hope you're all getting through midterms week all right. For us, like we mentioned, there is no midterm, but we're just going to be doing a week as normal, well, half a week as normal. And at the end of this week, I'm just going to report your current course grade as it stands. We will have an exam coming up. It's going to be the Tuesday right before spring break. So we'll finish up our exam. We'll have another day on Thursday, and then we'll be on an official break. So we're getting there. That means over this weekend, I'm going to start posting more information about the coverage, the definite content on the exam, and the review problems, those kinds of things. But other questions at the moment, folks, before we get started? Okay, well, we're taking a look at the inverse trig functions. Now, we're not inverting all 6 of them. We're focusing on sine, cosine, and tangent, which are the common ones that you'd work with. But really what's going on with these is we're going over to this section, common angles and radians, and we're just using this table going backwards. That's pretty much literally what we're doing. Before we jump into section 6.3, let's do a preview right here just to get a feel for how the action goes. So if you had a problem that asked you to calculate, let's make it be, say, a cosine inverse of, let's see, let's pick a good one. How about cosine inverse of negative root 2 over 2? So that could be our problem we want to calculate. Now, for cosine inverse, all of this is eliminated. Cosine inverse runs from 0 radians all the way to pi radians, or 0 degrees to 180 degrees. Exactly. So the idea is you take this number right here, negative root 2 over 2, that's about a negative 0.7. It would be here. And then you reverse engineer what is the angle that sends you to negative root 2 over 2. It would be this one, 3 pi over 4, like you mentioned. And then we're pretty much done. Cosine inverse of negative root 2 over 2 is 3 pi over 4. But for every single one of these problems, there is always a check as well. The check is just using the fact that if you're dealing with inverse functions and compare it with the ordinary function, all you're really doing is reversing the role of input versus output. So if you feel you have the right thing, then this should happen. Put 3 pi over 4 here. At 3 pi over 4, we get the value of negative root 2 over 2, once again. And that's why this is, in fact, correct. Negative root 2 over 2 goes right there. So there's a swap of input versus output. In fact, this is really very common. For example, if you take the square root of 16, we know that to be 4. Why do we know that? Well, if you take the squaring function and restricted still main, so it's actually 1-to-1 invertible, put the value of 4 here, you will get 16. So you have a pair of inverse functions. You're always swapping input and output every time you calculate in this kind of way. So just because it's trig, it doesn't mean it'll change. But what does change is how we get these values. We're grabbing them from the unit circle. So that whole spiel is just to say pretty much the goal of how we're going to calculate these things. That's also a reminder of why this table is so important. Memorizing this, if you haven't memorized it now, it's still plenty of time to do so, helps tremendously in trigonometry. Whether you're doing cosine or cosine inverse, this is basically the picture you want to have in your mind's eye. Well, any questions at all, folks, before we jump down to 6.3? Okay, let's take a look at what we left off there. We did exactly one problem, but hey, that's a good start to get us going. we're calculating sine inverse of negative root 3 over 2. But the first thing we have to observe is, for doing sine inverse, then sine itself is a restricted function with that domain and that range. That's why we went over here and said the domain should go from negative pi over 2 to positive pi over 2. Next, sine inverse itself has a swapped domain. This came from the range, and the range value here came from the domain, so those values do swap. And these are the only acceptable values you'll ever get as outputs to the function. Notice right away that this is pretty restrictive from -1 to +1. It means if I'm asking you for sine inverse of, say, -1.2, that's automatically undefined. You just cannot calculate that, because sine inverse has this domain. The minimum value you could ever put in is a -1. So this is undefined. So it turns out with sine inverse, cosine inverse, tangent inverse, this table right here for domains and ranges for the functions turns out to be really quite vital. Oh, if we go into complex numbers, then you can extend all of these domains and ranges to the complex plane. It gets wild out there at that point. Absolutely. Other questions or comments at the moment? Okay, well, let's give this next one a try. I think the next one is a little bit tricky. It's asking for arc sine of 0, or just sine inverse of 0. Keep in mind, sine inverse, arc sine are just two notations for the same exact thing. But anyone spot what this value should be? Sorry, say again. Exactly. That's what's weird about the domains and ranges. We have to take a value that goes in this band. Turns out 0 is the right value, because right here at 0, the sine value would be the first coordinate right here, which is 0. So that turns out to be a good, true equation. But every time you write down these, especially if you're practicing, we should also take a look at the check. If that's true, we should be able to take sine of where the red dot is, that's 0, and it should be equal to that 0, the input to the inverse function. Now, that is true, sine of 0 is 0. That means automatically arc sine of 0 is also 0. So if we relate what we know with what we're about to calculate, it helps out quite a lot sometimes. That was so fun. Let's just try it all over again. This one's asking for sine inverse of 1/2. So if you haven't spotted the angle, just go right here. Here's where 1/2 is. Then go off to the right. And we need this angle right here. See what it'd be? Sorry, say again. How about in degrees? Exactly. We have 30 degrees, or you could say pi over 6. And honestly, if you gave me 30 degrees, that is an acceptable answer. So if you're in an exam situation and you're just not sure what it is in radian measure, if you wrote it this way, it's non-standard. Be sure to include the degree symbol to make it totally correct. And at that point, it's just a change of unit. You have the right answer. But our text tends to focus quite a lot on radian measure, as would a calculus engineering class. So that's why we're focusing it in this way. And it is true that sine at pi over 6 is 1/2. So all we're doing is the unit circle backwards. We're starting on the y-axis for sine inverses and just trying to reverse engineer what is the angle that got us there. Well, let's keep on going. This one's saying sine inverse of -1. Anyone see what the angle should be for a -1 on this thing?
Is it 3 pi over 2?
Exactly. It would have to be the negative version, since that -1 would take us right here on the y-axis. And we just grab the angle negative pi over 2. And certainly, sine at negative pi over 2 would be that -1, right where the red dot is. And so if you feel like the check is almost kind of just saying the same exact thing, but backwards, That's awesome. That means you're getting a good feel for what the inverse functions are doing. Really, it's a pretty good review of chapter 5 in a certain sense. Now, here's where inverse functions get a little bit awkward, though. They also have properties, and one property is that if you take f composed with f inverse of a value x, there's an honest to goodness cancellation there. You just get x. So in other words, if you do sine of sine inverse of x, that's also a cancellation. You can swap where the inverse goes, but we also have to be very, very careful with domain and range. This one is potentially undefined. There's not a guaranteed cancellation here. If that was a 5, we would have said undefined immediately because it's calling the arcsine function. That means sine inverse. The domain is -1 to +1. So a 5 right there is an automatic undefined. But it was a 5th instead. So if you see a 5th right here, it's causing a cancellation with the inverse functions like we see on the right-hand side here. So sine with arcsine eliminates. And this one is just 1/5 altogether. It'll be through these properties right here that made it happen. Any questions about that at the moment? Okay, here's where it gets really weird. Now, you can change this around for sure. You could say, instead of f composed with f inverse, you can say f inverse composed with f of x. That's always x, as long as the x right here is really in the domain of the original function, relating it to sine and sine inverse. Sine inverse of sine at x would be x, as long as that x right there is in the domain of the restricted sine function. And it is not. So that's a problem for us. Another way to think about this is 7π/6 is not the answer because the range is here. The largest value you're getting is π/2. It does not actually extend to 7π/6. Well, this one doesn't have any cancellation at all. There's a mismatch on domain and range. Really very weird. But it is defined, and there's 2 ways to calculate this. I want to show you this shortcut, and then the longer form is probably the more stable way to go. Just order of operations. If you calculate sine 7π/6, then you can just follow your nose and do the sine inverse. But here's another way to think about it. Where is 7π/6? It's out here in the restricted range. That's why it's not the answer to this one. But if we draw it in, sine at 7π/6, and if I drew it perfectly, would match up with that value, the -√3/2, which would then match up to -π/6. And that should be our answer on this one. I think it is kind of a tricky shortcut, so let me show you an alternate way to think about it. Instead of all that, let's just calculate sine 7π/6 right there. So this is like the order of operations method. You would get sine inverse. And at 7π/6, I wish I didn't delete that angle. Here we are. The sine value comes out here at -1/2. My diagram just looks kind of weird. Yeah, absolutely. And I'm looking at my diagram and I think I'm seeing a problem here. Sine inverse of 1/2 is π/6. No, I think we're okay. Sorry, I think I'm just confusing myself. Yeah, you could use a reference angle approach on this one as well. Or if you're thinking in these terms, a sine inverse of -π/2 will give us a value of -π/6 altogether, which would be the reference angle coming from right over here, absolutely. But does that make sense to folks computing in those terms? Okay, I think this one right here definitely deserves like some kind of star or something, because I think this one is absolutely tricky to get through. Best way is order of operations. Reference angle works great. Plotting down this angle could help. But at the end of the day, the trouble is the restriction on the domain and range of that function sine, as well as the inverse, that caused no good cancellation to happen here. If it looked like this instead, if it was sine inverse of sine pi over 3, that's the normal one. There's no trouble with this. And why is that? Because sine pi over 3 takes us to this domain, and pi over 3 actually lives inside there. So this one has a cancellation. Can cancel here to here. The result is pi over 3. And we know that result would be correct because the function was sine inverse, and so pi over 3 has to be in the range right here for sine inverse, which it is. That means we're all set. That would be the right value for that function. Well, any questions at all, folks, with part F and the, I guess, part G down below that just sort of got written in? Okay, so this is basically the picture for sine inverse. We're only grabbing values from negative pi over 2 to positive pi over 2. But when you go to cosine inverse, it's a whole different story. It's kind of weird. Let's take a look at the graph just to get a feel for this. What we were trying to do is find a range for cosine upon which it stays 1 to 1. That's what makes it invertible. That range goes from 0 to 2 pi, or that is a typo right there. That goes from 0 to pi, not 2 pi. Let me fix that. Offending value goes from 0 to pi right here. So when we look at the restricted function for cosine, that's why you have a 0 to pi from the domain. It goes from a -1 to +1, so that's the range. And if you convert this to inverse, then everything swaps. The range becomes the domain for the inverse function, and the domain becomes the range for inverse cosine. So we have that common swapping for domain and range, input and output. But the picture down below is the reason why suddenly everything is different for the cosine function. It means if we're going to calculate on cosine, then the kind of diagram we would want would look a little bit more like this one. So here's a big unit circle diagram. Taking a look at the domain, we're only going from 0 to pi. So from here to here. That means everything down below in this direction is restricted. The only values we'll take go around this band, this upper half of the unit circle. With that set, we're pretty much ready to go. We want cosine inverse -√3/2. So what we do there is take the number, that's about a -0.9, goes right here. Then from that position, we find the angle that takes us to it. This angle turns out to be 5 pi divided by 6. Think of the pi right here as 6 pi divided by 6. It's 30 degrees short. That then tells us cosine inverse is nothing but 5 pi over 6. And then we did it, folks. That's the end on that one. For a quick check, just see if cosine 5 pi over 6 actually equals -√3/2. But it definitely does. We're in quadrant 2, so it should be negative. The reference angle is pi over 6, which produces the √3/2. And so, yeah, that's right. The input became the output, and this output is the input to the original function. If you have that common swapping, then that means your check is working as intended. Well, let's try this again. Anyone see what the value should be for cosine at 1 exactly?
Zero.
It wouldn't be, or excuse me. Yes, it would be 0, absolutely. Sorry about that. I was thinking pi for some reason, and that's a mistake. That would have been a -1 for the input. You're absolutely right. Cosine at 1 is 0. Let's write that out first. We know for sure cosine at 0 is 1. Sorry, I said that backwards. So if you swap these around, arc cosine at 1 comes out as a 0. So the truth of this function implies the inverse equation right here is also true. Any questions with that one? Okay, then looking down below to the next one, -1, keep in mind, if it's cosine, we're on the x-axis, and yeah, absolutely, that's the one that comes out as pi. I got that mixed up in my head, which is not a good idea. But here it is, this one comes out as just a pi. And just because we can, let's show the check. We do know that cosine of pi is -1. I mean, we're right here at pi, and the x-coordinate is -1 at that position. So observing it, how they swap means this is correct right here. So that's like 4 or 5 different functions at the moment. Let's take a look at some of the other ones. Next, it's asking for cosine inverse 1/2. There's a process. First thing you want to go is the horizontal axis. Find the position for 1/2. It's right here. Now reverse engineer by going up. And notice we have to go up because if you go down, you're in the forbidden zone. So there is a one way to do this. And we just have to find this angle now. Anyone recall what that angle ought to be? Absolutely. So pi/3 here, then comes down and we just say the whole thing is pi/3. And it's done on that one. And certainly if you swap it around, cosine at pi/3 really is 1/2. So we have accuracy on that one. Let's take a look at this one next. Cosine of cosine inverse 5pi/6. This one is not the dangerous one because note this 5pi/6 is in the domain of the cosine function, the restricted cosine function. So in other words, you could take a look at, it's up here rather, this table right here. If your 5pi/6 is in the domain of the function, and this is all you really have to do. There's a cancellation going this way, and this one is nothing but 5pi/6. Now, that is extremely dangerous as a process, though, because it's easy to write a problem where it just suddenly doesn't work. Let's see if we have one down below. We don't. Let's write down a problem where this wouldn't work and show how to work this out for a different version. But any questions so far, folks, with the inverse function canceling with cosine here? Well, it would if it was like a sine inverse. Oh, you're seeing this one right here. Yeah, this one is just undefined. Good call. The trouble with arc cosine at 3 is you're doing a cosine inverse function, and we've extended the domain by a lot, right? So this one is just automatically undefined right down here. So let's write undefined on this one. Now let's do a second version of part E, because sometimes they're nice and they cancel, but we need to be able to spot the ones where they are not so nice and there's some extra work we have to do on them. Let's say, for example, you're doing cosine inverse of cosine, and how about something random like, I don't know, 5pi/4. So every time you see cosine inverse with cosine, or vice versa, like down below, be very suspicious about domain and range each and every time. It's all about domain and range. This function 5pi, or this input 5pi/4, let's see, that's pi/4, 3pi/4, and 5pi/4 is right here. This means 5pi/4 cannot be the answer. A different way to look at it is the range only goes from 0 to pi, and those are the only equivalent or valid answers for a cosine inverse function. So we have to calculate this one slightly differently, but it's actually not too bad. Let me show you the trick again. Cosine of 5pi/4 gives you this value. That's -√2/2, but you can get to -√2/2 from right here at the angle 3pi/4. So my claim is that's just the answer immediately. Using a reference angle type approach, that's all you would have to do. Or the safest thing with this one is follow your nose with order of operations. It would turn into cosine inverse. Cosine at 5pi/4, we can't calculate that one. We get -√2/2, which is right here. But then cosine inverse of -√2/2, follow the red dot, is that value right at 3pi/4. Again, these ones are pretty tricky, so let's put a star on this one. And what I'm intending to print out on our next upcoming exam is this table right here. If you get used to looking at it, double checking it, seeing if things are in the right domain and range, it will be a massive support on the real exam too. But any other questions or comments, folks, on getting through these cosines? Okay, now we're ready for, in my opinion, what can be considered the trickier of the three. Cosine inverse has its own, oh, hang on, there's more. We'll get to tangent inverse in the next ones. But yeah, go ahead.
Why is where undefined?
Oh, this one right here? Oh, that one was because of this right here. It said, do arc cosine at 3, but if we're doing arc cosine, we want to look up right here. Arc cosine can only take an input as large as +1, so the moment they threw a 3 in there, it was undefined. Other questions at the moment? You betcha. Okay, well, let's try another one. I guess this was the trick question that I duplicated over here. I forgot I had a couple additional questions. Let's do another quick unit circle and try out these next ones. So we're going from 0 to pi, just because it says cosine inverse is what we're dealing with. I'll just kind of X out to that area there with some weird looking shading. And our values go from here to here. Now we want arc cosine of cosine negative pi over 4. But then that's a conundrum. Negative pi over 4 is this value. Exactly. That's going to be our value on this one. So the idea is we can't report this value, but we will go up to hit root 2 over 2 right here. So this is arc cos, or cosine inverse if you prefer. And this whole thing, cosine at negative pi over 4, turns into root 2 over 2. We come up and hit this value at about 0.7. But now that we have an input of root 2 over 2, we can keep on going up. And this right here, at pi over 4, is our answer to this one. So kind of a weird way to compute. But notice there's a pretty big shortcut here. You can go directly from here to here, absolutely. What you would want to do is place the angle, negative pi over 4, then go directly up, and the punchline is it was this pi over 4 to get us into the right range for cosine inverse. Well, that's a lot so far. Next one is asking for cosine 2.7163. This looks like it's just a rude question, but it's actually pretty fast. This is a restricted cosine function that goes from 0 to pi in its domain, and pi exceeds 3. So 2.7163 is in domain of the restricted function. That means that's celebratory worthy. You just cancel cosine inverse with cosine, and you get 2.7163. Now, the reason this one was undefined is because 3 was just not in the domain of arc cosine. But other questions so far, folks, with this one? Okay, so that's the wild adventures of dealing with arc sine, arc cosine, or sine inverse, cosine inverse. Next up is tangent, but tangent has its own definite oddities. It feels very different than sine inverse and cosine inverse. And to see what's going on, let's look at this table once more. We'll put the participants over here to the left. And now we're studying tangent x. The domain is indicated as being negative pi over 2 to positive pi over 2. And notice it has to be because the graph for tangent has vertical asymptotes. One at positive pi over 2, one at negative pi over 2. And that's why you see parentheses going around it. You can't actually plug in pi over 2 nor negative pi over 2 inside your tangent function. But the range on that thing is R, all real numbers. We might as well say here, just to be specific. When we use that symbol R, we mean from negative infinity to positive infinity. Now, why is that the range? That's because over here, it's going upwards indefinitely. And on this end, it's going downwards indefinitely. That's why we pick up all real numbers on this thing. Then it swaps. That means the domain of tangent inverse is any real number you would like. Here's what the graph would look like. And the range, well, it's positive pi over 2, excluding it, down to negative pi over 2, also excluding it. And you go from a function that has vertical asymptotes, your vertical asymptote transforms into a horizontal asymptote. And now negative pi over 2 is a value you cannot hit in the range of the inverse function. So weird stuff. This is really hard to keep in your head. That's why I'm going to include this table on the real exam too. So that means best way to study these problems is definitely keep looking at that table. That way you'll be familiar with it. You'll know how to use it come time for exam 2. Well, with all that in mind, here's the next batch of problems. Same table as before, but now we're just focusing on the last row for the tangent function. We'll do some evaluations, but in my opinion, tangent inverse is definitely a little bit harder. Sometimes there's a little bit more guesswork involved in finding the right angle. Practice helps, and this diagram also can help as well. Same as before, we're doing a unit circle, but I'm drawing this unit circle paying most attention to the range. That's how I drew all the unit circles on every one of those examples. I was looking at the range of the inverse function. These are the only outputs you could ever get for tangent inverse. Because of the parentheses, it's a good idea to put an open circle here. This conveys that pi over 2 is actually a value you cannot pick up. Another open circle says you can't pick up a negative pi over 2 either. Then all of this are values in the range of this sign for tangent inverse. So those are values we can really use. But on the left, these are now all excluded. Again, this looks like the diagram for sine inverse, but there's open circle at negative pi over 2 and positive pi over 2 being the main difference. So now let's give this a try. You know, other thing I'd probably put on this is, let's put down all the angles that could come up. They would be 0, pi over 6, negative pi over 6, pi over 4, negative pi over 4, and pi over 3, negative pi over 3. So there's altogether 7 possibilities for the answer. By elimination, we could find this thing, but we don't necessarily want to work that hard, right? We'd like to try to find it by doing as much elimination as possible. And that's already helpful. When it says that there's a negative sign, it means due to that negative, we're searching in quadrant 2 for part A, not in quadrant 1 at all. So these are temporarily all omitted values. I'll undo that X mark in a moment after we finish this problem. It's going to be one of these angles. A square root of 3 does come up, so that helps us. It probably won't be pi over 4 if a square root of 3 came up on this. Pi over 4 is conflated with getting positive ones or negative ones with tangent, cotangent, not root 3s. So that boils us down to those two values. It's either negative pi over 3 or negative pi over 6. I'm honestly not sure which one it is. Any volunteers for your best guess or your knowledge if you know? Here's what I would do if I wasn't sure. I would just try one and see what happens. And what I'm going to do is I'm going to start with a check on this thing. Again, tangent is a little bit weird. So let's start by doing tangent. And I'll just go down the line. Let's see what happens at negative pi over 6. If it works, awesome. If it doesn't, we'll go back to the drawing board. So negative pi over 6. And the numerator is the sine value for negative pi over 6. And that would be right here, negative 1/2. I already don't feel super confident. But hang on, I think rationalization might help us on this one. The denominator for negative pi over 6 is this value, root 3 over 2. It simplifies to negative 1 over root 3. And here's where rationalizing is actually a really, really good idea. You want to multiply by root 3 over root 3, because when you do that, the numerator looks like this thing, negative root 3. And so does the denominator. It comes out as a positive 3. That means it looks like we're on the right track with that thing. And it also means we have the answer. The answer is this, negative pi over 6. So tangent is a little bit special. Some people say it's a little bit annoying, and if you say that, I kind of agree with you. It does require a little bit of work. Some of it is guesswork, but usually there's not too much that you have to actually guess between if you're thinking of what's really eliminated. Tangent special, we'll take our time with this one and practice each one of these carefully. Any questions at all, folks, on getting that value? Okay, let's try it again. I think this next one is not as bad. Tangent inverse 0. Anyone see what a possibility could be? It would be 0, much like how sine inverse of 0 is 0. Tangent inverse has the same feature, but let's do the check just because we can. If that's the right answer, that 0 right there, we should be able to take tangent, plug it in a 0, and get a 0 back. So let's see, tangent of 0 would be sine of 0, divide by cosine of 0. That's a 0 over 1, which is a 0. And that says we're totally correct on that one. The zeros and the ones are sometimes a freebie. If you see tangent inverse of 0, it's just a 0. Now, if you see a positive 1 or negative 1, it's either pi over 4 if it's a positive 1, or negative pi over 4 if it were a negative 1. So there's some of tangent values that are pretty fast to calculate, but not all of them. Some of them are definitely pretty tricky, I'd say. That takes us to this thing, tangent arctangent 27. Let's take this with us as we think about that one. This one's kind of confusing because we saw something pretty similar to that. We did a problem that went cosine inverse of 3, and it is absolutely undefined. But that one isn't. That's kind of strange in a certain sense. Why is this not undefined? Well, if you go to arctangent, you're thinking tangent inverse. And if the domain is R, that means literally everything goes. There is no possibility for this format of a question with arctangent inside to ever be undefined. You automatically do a cancellation this way, tangent with the inverse function, and it outputs 27. At that stage, it's just completely done. But only arctangent has that feature. If this was sine arcsine or cosine arccosine, those are always going to be undefined. Does that make sense to folks on getting through this weird part C here? Okay, so sometimes the function and its inverse will cancel off. Other times it just absolutely won't cancel off, like on part D. And it's one of those weird issues where this 7 pi over 4 is not in range of tangent inverse. It only goes up to pi over 2, and 7 pi over 4 is way bigger. So let's just hit that with order of operations. We're expecting a reference angle of pi over 4, so we'll potentially see that reflected in the answer. But first we'll take tangent inverse. Tangent of 7 pi over 4 will become, let's think about that one. You will have a negative root 2 over 2. Let me get rid of that thing in the numerator. That's because 7 pi over 4 is this angle as well. And at 7 pi over 4, sine comes out as that negative root 2 over 2. Cosine is up here at positive root 2 over 2. And so this turns into tangent inverse of negative 1. But again, tangent inverse at 0 is nice. That's a freebie. And if it's a -1, the answer is -π/4. We'll always just grab that value right there. So this thing equals -π/4 altogether. Well, that's a kind of a tricky one, I'd say. Any questions, folks, on getting through part D? Okay, we have several more to go, so let's take a look. Next up is, again, to me, these are the nasty ones. It's kind of surprising, but you can always make some observations. Right inside here, we have a positive quantity, √3. That means all of this is off the table. You are now in quadrant 1 if there's a √3. It can't be π/4 because tangent of π/4 is a 1. We're dealing with a √3. So it's either a π/6 or a π/3. One or the other. If we grab it wrong, we'll just try the other one. Any volunteers for the decision? Should it be a π/3 or a π/6?
π/3.
Absolutely. That turns out to be the correct one. And there's a way you can kind of tell for this one. The problem up here confused me because this one's been rationalized and it kind of hid the fact that the √3 was in the denominator. But this one clearly has a √3 in the numerator. Sine at π/3 is a √3/2 back in the numerator, so it's directing us to that one. But let's start with a check. It's good to be absolutely sure we have the right thing because it can be so tricky. If we suspect it's π/3, let's take a look at tangent π/3. This equals sine π/3 divided by cosine π/3. These ones are nice. This is the quadrant 1 of the unit circle. Sine is going to be this value by the red dot, √3/2. Back to π/3, cosine is down here. This one would be a half. The denominators, divisions by 2's cancel, and you just get a √3. And that tells us we matched it up. If you find a √3 matches here, then this is your answer. Tangent inverse at √3 is π/3. Again, in my opinion, these are kind of tricky problems because it's not always clear how these eliminate, but the more practice you do, the easier it starts to become. This diagram's getting kind of busy. Let me take these temporary marks off. Okay, well, other questions, folks, so far? Looks like we have maybe one more. Well, that thing, tangent inverse -1. So if you see a -1 or a +1, it's either going to be this guy, π/4, or -π/4, right? Absolutely. The value of it being negative here directs us to quadrant 2, so that has to be our answer. So on this one, we will just pick up -π/4. And now I mentioned that tangent to me is pretty tricky, but the more you work with it, you'll realize π/4s only come up if it's tangent inverse of +1, -1. π/6 or π/3 only will come up if there's a √3 inside your tangent function somewhere. And if a 0 comes up, the answer is 0. There's actually not a whole lot of questions I can even ask on this, so you could actually practice every single potential version and get really fluent with what happens with tangent inverse. But I'd say this is the better approach as well. Just do the check first, throw that value in, and you're always going to be well on your way. Well, any last questions, folks, with the conclusion of this section? This went a little bit faster than I thought it would, but congratulations, everyone. We did it. That's the end of this section. I guess I have a question for folks then. We could take a look at the next section, or we can do one more slightly harder problem. Any volunteers for a direction to go? One more problem or the next section? Harder problem? Let's give it a try. To me, a harder problem would look like this. Calculate cosine inverse of sine of 1/3. What makes that a harder problem is I have no clue what sine of 1/3 comes out as. I don't have a good value for that. That's not a common angle that we work with. But it is in the right domain, so this is calculable. However, sine and cosine inverse, they feel like they're just not really conflating well. But there is a process for this kind of problem. Here's where we start. We take the thing that's confusing and we say, let theta be equal to sine 1/3. So that's going to be our start. Then if theta is sine 1/3, you know, this is an equation we can work on. Let's see, cosine inverse of the left-hand side, or hang on. I think I'm actually getting confused on this one. I have theta equals sine 1/3, cosine inverse over here. And I want to say cosine inverse equals some x value. You know what? I think I'm getting a little stuck on this one. That's kind of fun in a way. There's a way to proceed, but I'm not quite sure where it is. But that's just well as we can make this say an extra credit question. Let's open out a bounty on this thing. If you can solve this one, I'll give, say, 5 points extra credit on your homework score. Without a calculator, yeah, I want to see the full step-by-step process as if it was by hand. My hint is this, and I used to know how to do this, but I guess I might be just tired today. Forget how it goes beyond that step. What you want to involve is an inverse function, though. So let me see how far we can get on this. I was thinking cosine inverse, but that's not going to help us. How about sine inverse? That is a bit of a help. You can go sine inverse of theta equals sine inverse of sine of 1/3. If we go that route, that could give us something because we at least know that from here and here, that's a true cancellation. And we now have that sine inverse of theta equals 1/3. But again, I'm not sure if that's the right approach on this one. There's got to be a different way to go to get through this. So let me back off to this step. And again, I'll think about this one. If you decide to attack this problem as an extra credit question, I'll be very happy to help out. I think I just need a little bit more sleep to recall exactly how this one goes. But this is a real extra credit question. I'll give 5 points on your last homework assignment when you decide to go for this one. And it's going to be to find the exact value of this thing right here. It's going to be equal to some value, but it's going to be an angle. Well, other questions or comments about it so far? Let's maybe try one more thing. That could be a valid approach. So if you use other extraneous approaches from this class, I'd be happy to see it as well. That could be a fun way to look at it. I'm thinking on this, how about if we go cosine inverse? We said theta is this location. And we can say cosine inverse of sine of 1/3 is the theta equals, it's an unknown, so how about x to start? If you went that route, you could take cosine of both sides of this. Well, again, I think I'm getting stuck on this one. There is a pretty good approach to calculate a problem like this one. I think I'm just drawing a blank. So I'll leave this one as an open extra credit question. Oh yeah, factorial, that can be done, but now you need the gamma function to make that work. Factorial function is actually extended to be any number you want to put in that's positive. So it can actually be done, as weird as it sounds. But I think this is a good stopping point for us, folks. Think of part F as the last official problem in this section. And this one is just for fun. I'll be happy to come back to it if you decide to work on it. But have a great weekend, everyone. It's the end of midterm, so congratulations as well on that. Any last questions before we call it a night? Okay, well, see you all later on next class on Tuesday. And I'll start putting on Moodle over the weekend before Tuesday's class, more information about what's going to be on exam 2, the formula sheet that will be provided and that kind of stuff.
Actually, I have a question.
Yeah,
On letter H, the inverse of cosine 2.7163. Why is it equal 2.7163 and it's not undefined?
that's because of, let's go right here for this table. And let me also put a problem right down below it to kind of clarify as well. If it went cosine of cosine inverse 2.7163, now we have a totally different situation. But let's look at this one first. 2.7163 was going inside a cosine function. So that means we're using this right here. And pi being 3.14 says that's in domain, allowing the cancellation. But notice how tricky that is. If you put the -1 power right here, so the inverse is on the inside, 2.7163 is now relative to that domain, and now it's suddenly out of domain.
Yeah.
That's what makes it undefined. And to me, that's what makes all of this extremely tricky. That's why I find some comfort in this table, because when we get used to using it, it clarifies a lot of these tiny, tiny subtleties. Like this one right here being suddenly undefined. Does that make sense for that question?
It does, thank you.
You betcha. Any other questions, folks, before we call it a night? Okay, well, have a great night, everyone. I'll see you all next week. It'll be 2 more weeks and then we're on spring break, so we're just about there.
Thank you.
You betcha. Have a good one. So that's the Maclaurin series for sine. It's an odd function, so you should have odd right there. That's how I kind of remember them. But then from here, and you put the 1/3 into that location, coming from that one. Sorry, say again? Yeah, exactly. You did have the X, it's right there. Yeah, so now you've got 1/3 to a power there with an infinite sum. There could be something you could work through there, but I'm drawing a blank on that approach. It's cool to know that that's a valid way to think about it though as well. Sorry, say again? Your calculator should actually be able to do it exactly. It should be able to give you the exact value on that kind of thing. But, you know, when I'm looking at this, possibly the reason I'm drawing a blank on it is I wonder if when I invented this problem, I should have had the inverse symbol right here on sine as opposed to cosine. So I'm going to possibly come back to the drawing board on that one and let you all know if I made a misconfiguration of where my inverse went. Sorry, say again? Yeah. I'm almost suspecting though that if you want to try this in a different way with the inverse on sine, but not on cosine, I'm thinking that's why I was getting a little bit confused. I put the inverse on the wrong spot. Sorry, say again. Oh, wait. Came out as, yeah, it's a good. Yeah. Cool. Yeah, some kind of fraction. I almost would think it's, yeah, this one is kind of weird. Degree mode is exact at degree mode. That's kind of weird. I wonder if that's a coincidence of some kind. That's interesting. What did it come out exactly as? Yeah, repeating 89 something. Interesting. Gotcha. So that would be the angle, almost 90 degrees. That's kind of interesting. Yeah. 5 or 2, right? Well, I think that was a good problem to try at least. It's definitely food for thought.
All right, y'all have a good night.
You too. Don't work too hard.
Just beginning.
Yeah. See you later.